Good day, friends. Today we will talk on linear algebra, the branch of mathematics that started with how we deal with linear equations. So today we'll talk on linear algebra. Linear algebra is a branch of mathematics concerning linear equations such that a1x1 plus a2x2 plus an equal to b. So we have n equations, n unknowns, the simultaneous equation, and we apply linear algebra matrix theory to solve them. It could also be seen as the map of the point x1, x2, xn, the integral in the n-dimensional space, a point that maps to the real number a1, x1 plus a2, x2 plus plus an, xn. Linear algebra talks about these maps also, and the representations in vector space and through matrices. As an introduction, linear algebra is central to almost all areas of mathematics. For instance, linear algebra is fundamental in modern presentations of geometry, including defining basic objects such as line, planes, and rotations. Also, functional analysis, a branch of mathematics and analysis, may be viewed as the application of linear algebra to function space. Functions could also be an element of linear algebra. Linear algebra is also used in most sciences and fields of engineering because it allows modeling many natural phenomena and computing efficiency with such models. For nonlinear systems which cannot be modeled with linear algebra, it is often used for dealing with first-order approximations using the fact that the differential of a multivariate function at a point is the linear map that best approximates the function near the point. We talk about the tangency, the gradient, and those would have linear treatments. We start with vector space. Until 19th century, linear algebra was introduced through system of linear equations and matrices. In modern mathematics, the presentation through vector spaces is generally preferred since it is more synthetic, more general, and conceptually simpler, although more abstract. Talk about a vector space, we talk about a set V with an operation plus with an operation plus, which is a binary operation. So for two elements V plus W in V plus the vector space is closed under operations, and there are some more axioms about it. The associativity of addition U plus V plus W is U plus V plus W. Commutative addition U plus V equal to V plus W. This is known as abelian operations. Also, it is to show that whether vector space is commutative or not. Say matrix multiplication is not commutative. So vector space need not always be commutative. Identify element of addition. There exists an element 0 in V called 0 vector such that V plus 0 equal to V for all V in 0. The identity element 0 is important. Inverse element, for any V in V, there exists an element minus V in V called the additive inverse of V such that V plus minus V equal to 0. So when we get an element V in vector space, we also have its negative, its inverse. Then we have distributivity of scalar multiplication with respect to field addition, compatibility of scalar multiplication with field addition, field multiplication, identity element of scalar multiplication 1 into V equal to V, where 1 denotes the multiplicative identity of F. That's another operation, multiplication. Together with addition and multiplication, the real line forms a field. That's why it is called field operation. The first four axioms mean that V is an abelian group under addition. Some examples: an element of a specific vector space may have various natures. For example, it could be a sequence, a function, a polynomial, or a matrix. Could be an element, or the numbers. Numbers are also could be elements of vector spaces. Linear algebra is concerned with the properties such objects that are common to all vector spaces. Now we construct the vector space and observe its properties through various operations. There are some more applications. Application in functional analysis. Functional analysis studies function spaces. There are vector spaces with additional structures such as Hilbert spaces. Linear algebra is thus a fundamental part of functional analysis and its application, which include in particular quantum mechanics, wave functions, and Fourier analysis on orthogonal basis. Then some scientific computation. Then geometry of ambient space. The modeling of ambient space is based on the geometry sciences concerned with the space with geometry widely. I'm not very conversant about ambient spaces, but there is an application of linear algebra. Study of complex systems. Most physical phenomena are modeled by partial differential equations. To solve them, one usually decomposes the space in which solutions are searched into small, mutually interacting cells. For linear systems, this interaction involves linear functions. For nonlinear systems, this interaction is often approximated by linear functions. This is called the linear model or first-order approximation. Thermal energy system. I'll stop here. I haven't talked about the quantum mechanics where linear algebra is essential, or the machine learning, or the generative AI where the basic mathematics of those fields heavily use linear algebra. I'll stop here. This talk is completely based on the Wikipedia article on linear algebra. Like, comment, share, and subscribe. I am available for one-to-one sessions too. Thank you.